Welcome to Unit 7, Inference for Quantitative Data with an emphasis on means. In this video, we're actually going to cover two topics. I know we've never done this before, but we're going to cover topic 7.8, setting up a test, and 7.9, carrying out a test for the difference of two population means. In the past, I've actually been separating these topics, or these topics are actually separated, to go over kind of like steps 1 and 2, and then steps 3 and 4 of the process of a test. But to be honest, I feel like this is the fourth time we've done this. We did this with proportions. We've done this with the difference of two proportions. We did this with a single population mean, and now we're ending it with a difference of two population means. I just feel like it's just redundant if I do two videos, one for steps 1 and 2 and one for steps 3 and 4, because by now we should know the concept so well that we could just maneuver through it very, very quickly. All right, so what are we going to learn in this video? In this topic, we'll be exploring how to run a two-sample t-test to determine if there is a difference between two population means. So we're going to look at a mean from population 1 versus a mean from population 2. Now, keep in mind, we're not looking at different means. We're not looking at the mean weight of giraffes, and then we're going to look at the mean height of elephants, right? We're not doing that. We're going to look at the same value. For example, we're going to look at the mean weight. The mean weight of black bears, that's population 1, versus the mean weight of brown bears, that's population 2. Or we're going to look at the mean IQ of boys, population 1, girls, population 2. So keep that in mind as we're going through this, okay? But there's definitely two populations, and we're comparing the same value from those two populations. Now, to do this, the only way I could think to figure this out is to start with looking at a sample, right? We need to take a mean from a sample taken from population 1, and we need to examine a mean taken from a sample from population 2, right? So we're going to look at an X bar for sample 1. So that's a mean of a sample taken from population 1. And we're going to look at a mean of a sample taken from population 2. So the key thing here is that we definitely have two different populations in two separate samples, one taken from the first population, one taken from the second population. Now, the whole point of topics 7.8 and 7.9 is to ask ourselves, okay, is there a difference between these two populations? Now, to explain how we're going to tackle this, I really need you to understand this first and foremost. Anytime you have a mean from one sample and a mean from a second sample, let me just give you something important to understand. These two numbers are going to be different. They just are. I mean, what are the chances that you take a mean from one sample and a mean from another sample and they're exactly the same to the 14th decimal place? It's just not going to happen. These two numbers are going to be different. There is going to be a difference between your two samples. I can tell you that much right now. But the question is, why are we seeing a difference? And there's two reasons for this. There's two possible explanations for why we're seeing a difference between these two values. The first is that we're seeing a difference because of just simple random variation or random assignment. Anytime you look at two samples, they're going to vary. I mean, the one thing we've been saying all year long is that the one thing samples do very, very well is that they vary. Samples are always going to vary. So maybe we're seeing some differences between these two samples because it's just natural variation that exists when you sample. They're different because they're just different. It's not anything you're in control over. Or maybe these two samples are different because there really is a difference between the two population parameters. There really is a difference between mu1 and mu2. There's really a difference. Hence why there's really a difference between the samples. Because remember, a sample should reflect its population. A sample should reflect its population. So maybe I'm seeing such a difference between these two numbers because there really is a difference between their populations. So that's what we have to decipher. Is the difference we're seeing between our two samples just pure randomness for randomness' sake? What are you going to do? It's just part of sampling. Or is there a difference between our two means because there's actually a difference between the two populations? And that's what we have to answer. And it's all very simple because we've been doing this before, right? We've explored this idea. It's very simple. If we deem the difference to be not significant, well, then that just simply means that the difference was probably just due to pure chance. Nothing we could do about it. It doesn't mean anything. But if we deem the difference between our two samples to be significant, then that is what tells us that there is an actual difference between the two population parameters, in this case, the means. Now, let me give you like a really simplistic idea of this, just so you understand, okay? Let's just say our first mean from our first sample drawn from our first population is 7.1. And let's just say that the mean from the second sample drawn from the second population is 8.0. Okay, that's a difference of 0.9. And that's what we are going to explore. Is that difference of 0.9 significant or not? Is 0.9 such a little difference that it's just probably because of sampling and these two populations aren't different at all? Or is 0.9 such a big difference that it's so significant that it tells me that these two populations really are different? And that's the whole point of why I'm teaching you this video, right? You can't just look at that and say, oh, well, 7.1 is different than 8.0, case closed, the populations are different. No, it's not quite that simple. We have to really explore that 0.9 difference and determine if it's significant or not, and that's exactly what I'm about to teach you to do. And it's called a two-sample t-test for the difference between two population means. And of course, to complete all of this, there's 4 very, very well-known steps. Name the test, give the hypotheses, check the conditions and build that sampling distribution, find the t-score and the p-value for our difference, how special is our difference or unspecial, and then give a conclusion. We should be very, very familiar with these steps. So technically 7.8 is steps 1 and 2. And then steps 7.9 is steps 3 and 4. But like I said, I think we've learned all this enough that we can put it all together in one video here and save you some time. All right, so let's talk about step 1. Step 1 is first off naming it. This is a two-sample t-test, the difference between, and then you got to fill that in with some good context. This is a two-sample t-test for the difference between the weight of black bears and brown bears. Okay, fill this in right here with good, solid context from the problem. All right, then we actually need the null and the alternative hypotheses. Now, the null is, hey, there's no difference. Well, if you're seeing a difference, it's probably just natural variation. There's no difference. So if there's no difference, the null would be that the two population means are equal. Now, I prefer this right here, just saying mu1 is equal to mu2. But again, this other statement over here that I'll put in red, this is the same thing, right? Because if they're equal, then the difference would be 0. I mean, that should be common sense, right? Just subtract the mu2 over, and if two values are equal, then that is telling you that the difference between them is 0. I don't really care which one you use, but I do prefer the one I circled and starred there. All right, so the null is that these two population means are the same. The mean weight of black bears, it's equal to the mean weight of brown bears. They're not any different. Now, the alternative is what we are wondering, right? Or what the fictional character in the problem is thinking. Now, there's 3 different options here. Maybe somebody says, no, I think black bears are definitely bigger on average. They weigh more on average. So I'd use a greater than sign there. Or maybe says, no, I think black bears are less than brown bears. Or maybe somebody says, you know what, I don't really care who's bigger or who's smaller. I just care that they're different. They are not the same. So this is called a one-sided test. This is also called a one-sided test. And this is what we call a two-sided test. Now remember, the only thing you have to do different when your alternative is not equal to is just multiply your p-value at the very end by 2. All right, step 2 is to build the sampling distribution. Now, this is probably the most important step, but for some kids, it just kind of goes under the radar. Because what I want you to understand right now is that we're not making this decision about the populations based on just 2 samples. And I know that that's what it seems like, because that's kind of what it is, but that's not the truth. Remember, we're building a sampling distribution. We're not making the decision based on just our difference. what we're doing is we're building that sampling distribution, showing us all possible differences between two samples. And we're seeing where our difference fits in. So yes, we only have our two samples, but we're comparing them to all possible differences. That's why the sampling distribution is so vital in this process. All right, so we do have to build that sampling distribution on the assumption that the null is true and that there really is no difference. So we do have to check our three conditions. The two samples have to be random and independent of each other to avoid bias. Both samples have to be less than 10% of their respective populations from which they were drawn to assume independence. And both samples need to either be greater than or equal to 30, or if not, we do need to check our data and make sure that each set of data, sample 1 and sample 2, has no major outliers or no major skewness. Now, I will say this, and I say this with a little bit of worry, but in an FRQ, if you do have a sample less than 30, I'm going to tell you right now, it probably will work out, but you do have to officially check and make sure there's no major skewness or outliers. But this becomes a great multiple choice question, where somebody might say, hey, is this good? Can I build a sampling distribution? And maybe you look at this and it's drastically skewed to the right. And in that case, you would say, whoa, no, my sample is under 30 and it's very skewed. I should not be using a sampling distribution in this problem. But that's probably not going to happen in an FRQ. In a multiple choice, it could. But again, you technically need to be checking if you're under 30. Now remember, if you're greater than 30, you're good to go. Okay, you don't have to worry about anything because of central limit theorem. All right, so just remember, when we build that sampling distribution, we technically need three things. We need the mean, the mean of it, the standard error of it, and we'll talk more about why we can't use standard deviation in 1 second. And we need that beautiful shape, which again is going to be a T, and that all kind of connects to what I'm going to talk about right now. So first, the center, the mean of all possible differences. Remember, sampling distribution doesn't just show you your difference, it shows you all possible differences. So the mean of all possible differences, any possible difference, right? That's what this is right here. All differences, the mean of all differences should be 0. Because think about it, if the null is true and there really is no difference, then some differences are naturally going to be on the positive side, some are going to be on the negative side, but if there's truly no difference, then the mean of all the differences should show you that and have a 0 smack dab in the middle. Now, I would love to use standard deviation. In fact, when we first learned about sampling distributions back in Unit 5, we did use standard deviations, but standard deviation requires the true standard deviation, sigma, from each population, and I'm sorry, I don't have those. The only thing I have is the standard deviation from each sample, S1 and S2. Those are my sample standard deviations. So because I'm replacing sigma with S's, that's why I have to call it standard error, and that is why this needs to be a T model and not a normal model. Okay, but thank goodness we have TCDF and invert T on our calculator, so it's not really that big of a deal. But we do have to know this is a T model. It actually is more accurate, which is why we're using it. So once we calculate the standard error, we could then build our sampling distribution by going up 1, up 2, up 3, down 1, down 2, down 3 standard errors. I'll also say this, a picture of the normal, oh boy, I almost said normal model. A picture of the T model is not a requirement, but you do have to have the mean and the standard error. You could visualize the picture. I personally like making the picture because it allows me to see where my difference falls. But obviously the T-score is going to help us find that as well. All right, so let's move on to step 3 here, finding the T-score. So now it's time to locate the difference we observed, right? So this is where we're going to say, okay, we have this model that shows me what all differences should look like, and now where's our difference at? So we're going to take our difference between our two samples, x1 our x bar minus x bar. We're going to take our difference between our two samples, and we're going to subtract the null. Now remember, the null was that there was no difference, so subtract 0, but that doesn't really do anything because that's the mean of the sampling distribution, 0. And then we're going to divide by the standard error in the denominator there. So that's going to give us our T-score. That's going to tell us where our sample falls. And to be honest, usually with that t-score alone, you could get a pretty good feel for, oh, wow, I only have a t-score of 1.1. Well, that's not very big at all. That's not significant. Now, a t-score of 6.9, oh boy, that would be significant. And that's why kind of the t-score does help you understand where you are. But the p-value is really what you need to make your conclusion. So how do we find a p-value? Well, remember, a p-value is the probability of any other difference being more extreme than ours. Now, I use the greater than sign, so if your difference is positive, then more than that would be greater than. If your difference was negative because you did it in the other order, where you subtracted your means and you got a negative, then you would be looking below, less than, okay? But I typically like to purposely subtract them in a positive manner to create a positive number. But it's up to you. You really can do it either way. Just know that if it's negative or more extreme would be lower, not higher. All right, so once you understand a p-value is the probability of our observed difference, it's the probability that any other difference is more than our difference, okay? And you're going to find that by doing the probability that a t-score is more than our t-score. And of course, we're going to use TCDF to do that. Now, a couple things to keep in mind here. When you do use TCDF, you do need degrees of freedom. Remember, how do you get degrees of freedom with two samples? Well, you're going to take your first sample size minus 1. You're going to get the degrees of freedom from your first sample. So take your second sample minus 1, get your degrees of freedom from your second sample, and then whatever one of those is smaller, that's the degrees of freedom you use. Now, we did talk about in previous videos that that's actually not the proper technique for degrees of freedom, but it is acceptable in this class. To get the official degrees of freedom is way too complicated of a formula when you have two samples. So we just find the degrees of freedom for each sample and use the smaller of the two. All right, now it's time to make our conclusion. And again, this should be something you should be familiar with. But remember, we make our conclusion based on comparing our p-value to our level of significance, which is our alpha value. So remember, you're either going to be given the alpha value in your problem. You'll be told to use 1 or 5%, or if it's not there at all, then you get a pick. It's completely up to you. But usually you're going to be given 1 or 5%. All right, so if your p-value is less than the level of significance, this means that your difference was significant. And remember, if you deem your difference significant, that is telling you that there is a difference between these two populations. So if your p-value is less than the level of significance, this means that the difference you observed was significant. The proper conclusion is to reject the null. And when you reject the null, that means that there is evidence that the alternative is true. So there is evidence of a difference. Now, if your p-value is greater than the level of significance, then this means that the difference you observed between the two sample means is not significant. And that means that it was probably just due to chance. It really didn't mean anything at all. So the proper conclusion here is to fail to reject the null and say that there is not enough significant evidence that the alternative is true. So we are not concluding that the null is true. We're just saying that there's not enough evidence to say otherwise. And that's been the kind of the common thing we've said for a long time now, is that when you fail to reject the null, that's not equal to accepting the null. We just do not have evidence to go against the null. Okay, so, I mean, guys, that's it, right? That's all 4 steps. I told you I could do it pretty quickly in one video. Now we just got to look at some examples, and I think you'll find these examples quite simple. All right, the first example is, are student athletes smarter than non-student athletes? Good question. All right, to find out for students at his school, Max selected a random sample of 32 student athletes and 40 non-student athletes. The mean GPA of the athletes was 3.05 with a standard deviation of 0.75, and the mean GPA of the non-athletes was 2.98 with a standard deviation of 1.02. So does this evidence indicate that student athletes have a higher GPA on average than non-student athletes? Run a test at the 5% level to find out. All right, so the first thing I like to do is, there's a lot of numbers in this problem, so let's organize this. So let's talk about athletes. The athletes had a mean of 3.05, a standard deviation of 0.75, and a sample size of 32 athletes. All right, my non-athletes had a mean GPA of 2.98 and a standard deviation of 1.02, and I looked at 40 non-athletes. Now, if you look at these two numbers, that's a 0.7 difference, okay? 2.98, or I like to always subtract to keep things positive, so 3.05 minus 2.98 is a 0.07 difference. Sorry if I think I might have said 0.7, I meant to say 0.07 difference. So this is what we have to answer out. Is a 0.07 difference significant? Does this show us that athletes do have a higher GPA on average, or is a difference of 0.07 so minuscule that it probably was just due to chance, and this doesn't say anything that athletes are smarter by any chance? So that's why we're going to actually do this work. All right, so first, step one. This is a two-sample t-test for the difference in the mean GPA between athletes and non-athletes at Max's school. There you go. Just make sure you give that nice context. Now, I'm going to use some subscripts here. Don't use generic 1s and 2s. So my null is that there's no difference. The mean for athletes is equal to the mean GPA for non-athletes. But the alternative is what Max is trying to figure out. Excuse me. Max is trying to figure out, are athletes smarter? Do athletes have a higher GPA? The question clearly said that. So that is our alternative. All right, now step 2 here is our conditions and building the sampling distribution, assuming the null is true. So just kind of run through these real quick. Both samples and athletes, non-athletes are independent and random to avoid bias. I will assume that 32 athletes is less than 10% of all athletes at his school. I don't know for sure that's true. That's why I haven't used the word assume there. 40 non-athletes, I would also assume is less than 10% of all non-athletes at the school to assume independence. Both samples are at least 30. Both samples are 30 or more. So it's safe to use a T procedure for a two-sample means with 31 degrees of freedom. So the athletes had 31 degrees of freedom. The non-athletes had 39. I'm going to use the small of the two, 31 degrees of freedom for my T model here. All right, so when I build that sampling distribution, I have to build it on the assumption that the null is true. That means that the mean of all possible differences should be 0. And the standard error is going to be taking the 0.75 squared divided by the 32 athletes plus 1.02 squared divided by the 49 athletes, giant square root around all that, and we get 0.2088. So I went up 1, 2, 3 standard errors, down 1, 2, 3 standard errors. Again, you don't need that picture, but I think it really helps because before I even do step 3, remember the difference we saw, the difference we observed was 0.07. 0.07 is right around here somewhere. So I'm going to tell you before I even do the next step, that does not seem to be a significant difference at all. But that's why drawing the picture helps, because I can actually see that somewhere around 0.4 would be where I would start to think of, whoa, boy, that's a pretty big difference. Anything below that is really not. But again, I do need the t-score and the p-value to verify that. All right, so here's the t-score. The t-score is taking my difference, 3.05 minus 2.98 minus 0. Why 0? Because that's the center. That's the mean of the sampling distribution. So I'm going to take my difference, 0.07, divide it by the standard error. And like I told you, this is not very big at all. So 0.07 is a t-score of about 0.3352. So it's not very big at all. So the probability that a sample difference is more than mine is the p-value. So the probability that any other difference between athletes and non-athletes is more than 0.07 is the probability that a t-score is more than 0.3352. To do that on my calculator, I'll show you guys this real quick. If I am going to grab TCDF, second vars, TCDF is number 6. And I'm going to go from 0.3352. Sorry, having a calculation there. 0.3352. And then I'm going to use 99 to act as my infinity. And then don't forget the 31 degrees of freedom right there where it asks. And I get a p-value of 0.3699. So again, that is very, very high. That is not significant at all. That's telling me that the probability of seeing a difference of 0.07 is very likely. It's not weird. It's not strange. It's certainly not significant. So since my p-value of 0.3699 is way bigger than 0.05, I will fail to reject the null. There is no significant evidence that the mean GPA of athletes is greater than the mean GPA of non-athletes at Max's school. Yes, our sample did show athletes were a little bit higher, but it was probably just due to sampling. If I did it with a different sample, it might even come up where the non-athletes have a higher GPA. There is clearly no evidence of a significant difference. All right, let's jump right into example 2. Example 2 says, do people who exercise frequently have a lower resting heart rate than those that don't exercise? So to investigate this, Melissa selected a random sample of 10 people who claim to exercise 4 or more times a week for more than 1 hour. She also selected a random sample of 8 people who never exercise at all. The results of their resting heart rates are in the table. So for the exercise group, I had 10 people. Nice table here giving me all of their heart rates, but the mean was 60.1, and that had a standard deviation of 7.0309. For the non-exercise group, all 8 heart rates are there, and I'm giving you the mean, so you don't have to worry about doing it, but the mean was 79.625, and that's a standard deviation of 4.9839. So just kind of looking at the means right now, it does seem that the exercise group is roughly 19 beats per minute lower. Now, is that a significant difference? Well, that is what we're going to try to figure out. So does this data provide significant evidence that people who exercise have lower resting heart rates? And they want me to use an alpha, a significance level of 1%. So step 1 is giving it a good name. This is a 2-sample t-test for the difference between the mean resting heart rates of people who exercise regularly and people who do not. Please make sure that you have the difference between the mean and then give me all that nice context. Now the null is, of course, there's no difference. There's no difference between the average heart rate for those that exercise and the average rate for those that do not exercise. They're the same. They're equal. Doesn't matter. And the alternative is that what I'm wondering, I'm wondering is the mean for those that exercise truly lower, less than the mean for those that do not exercise? All right, my conditions I know are boring, but we got to do them. Both samples are random to avoid bias, and they're independent. I assume that both samples of 10, the people who exercise are definitely less than 10% of all people who exercise, and then 8 people who do not exercise is less than 10% of all people who do not exercise. Now here's where I'd have into a major issue. Both samples are way less than 30. So I want to just show you what you should be doing. You should be entering this data into your calculator, stat edit. Let me see here. I have the data entered into list 4 and list 5. So list 4 are my exercisers, list 5 are my non-exercisers. So what we need to do is just make sure the data is not skewed or any major outliers. So I'm going to go to second y equals. I'm going to turn plot 1 on. Let's take a look at my exercise people first, which is list 4. And now remember, the zoom we like is a zoom 9. This is the zoom on our stats. And I mean, I don't really see anything. Can I say that's majorly skewed? Well, I mean, somebody might want to argue that with me, but remember, there was only 10 people in the group. I mean, I wasn't expecting to see anything beautiful anyway. Yeah, it doesn't look great, but I don't see any major skewness. I mean, major skewness is where you see a slow step down, 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 down. I don't really see that here, and I don't see any major outliers either. It doesn't look beautiful, but it doesn't really signify anything weird is going on here. And then now let me check out my non-exercise group, and for me that was list 5 is where I entered them in, so second number 5. And then quit out of there and do a zoom stat, zoom 9. And again, no major skewness, no major outliers. I mean, it's only 8 people, but I mean, I don't really see anything that concerns me. I always tell kids, if I want you to see major outliers and major skewness, trust me, you will see it, okay? So since both graphs looked okay, we are okay to proceed with 7 degrees of freedom for my T model here. Obviously, I'm choosing the lower of the two. 8 minus 1 is 7, 10 minus 1 is 9, 7 is smaller. So anyway, the mean of my sampling distribution, assuming the null is true, is 0. I'm going to assume that there is no difference between those that exercise and those that don't. My standard error is taking my standard deviations. Don't forget to square them. A lot of kids forget to square them. Divided by the sample size for each. And I got 2.8369. I went up, 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 down, down, down. Now, if you remember, our difference was negative 19. Now, that was just kind of spitballing it, but if you look at the difference, it was 60.1 for the exercise group, 79.625 for the non-exercise group. That was a difference of roughly negative 19. And if you look at the picture I made, that is clearly significant. That is way off the chart. But we do need the t-score and p-value to confirm that. So my difference was the 60.1 minus 79.625. Again, there was a difference of exactly negative 19.525 divided by my standard error, 2.8369, and negative 6.8825. That is way down here somewhere, clearly significant. So the p-value is the probability that a difference is even lower than mine. The probability that any other difference between two groups, exercise, non-exercise, is lower than mine, more extreme than mine. That's the probability that a t-score is even less than mine. So I use TCDF here. I'm going to start at negative 99 as my negative infinity. I'm going to go to negative 6.8825, my t-score. And again, don't forget the 7 degrees of freedom. And the p-value is really, really low, 0.000175. This is clearly a significant difference. And this is what's going to clearly tell me to reject the null. Since my p-value is well less than my alpha, I'll reject the null. There is significant evidence that the mean resting heart rate of people who exercise regularly is lower than the mean resting heart rate of people who do not exercise regularly. So pretty clear evidence here that I'm making the right decision to reject the null. And it does appear that if you exercise, you do have a lower resting heart rate on average than somebody who does not. All right, guys, that's it for the video. Hope it was fairly quick and painless and that everything made sense to you and that you can now go through some practice problems on your own, kind of following my procedure here and making sure that you can make an appropriate conclusion looking at the difference of two sample means.